Now, as far as the necessary and the sufficient condition of the deadlock is concerned, we already know that we have seen in the resource allocation graph that if there is a cycle that is going to give the necessary condition that there will be existence of a deadlock. It means if any resource allocation graph, if there is a cycle, then there is a possibility that that system is going to be in the deadlock state. But if the graph is showing in such a manner that there is no cycle, it represents that a state that is free, the system is free from the deadlock. But on the other hand, if the graph contains a cycle, the deadlock may exist. It may exist, it may not exist, depending upon the certain condition. So just the presence of a cycle in a resource allocation graph, it may be a necessary condition, but it is not a sufficient condition for the existence of the deadlock. Now, if you take an example of the resource allocation graph in which it seems that they are in the deadlock state, but actually it is not so. Now it contains a cycle. This graph is containing a cycle that is P1, R2, P2, R1, and P1. But there may be a situation that it is not in a deadlock state. Now, what is happening? This particular resource is having one unit. This particular resource is having two units. One of the unit of this resource is assigned to P1. Another unit is assigned to P2. And P2 is requesting for the resources from R1. Now, R1 has two units. One is assigned to P1 and one is assigned to P3. Now, why it is not in the deadlock state? Because R1 is having two units and both the units are allocated. Now, if P3 finishes its job, it will give a release message to R1, and if P2 is in the waiting state requesting for R1 and P3 has released, so the second unit of the R1 will be available to the P2. So it means the request edge will be converted into the assignment edge. Now, at that time P2 will be having assigned R2 as well as R1. When P2 finishes its job, it will release R2 as well as it will release the R1. Now, once these two are released, R1 is already allocated to P1 and R2 will also be allocated to P1. So P1 will be finishing its job. So after P3 is going to finish its job, P2 is being assigned and P2 is going to finish its job, R2 will be allocated to P1. So this is the condition in which you can say that it is not a deadlock condition. So that is why the presence of the cycle may be the necessary condition for the deadlock, but it is not the sufficient condition for the deadlock. So there are two situations. For the two different cases, the sufficient condition can be suggested. The first is a cycle is necessary and sufficient condition if the resource type have a single unit each, meaning thereby a cycle in a graph is both a necessary condition and the sufficient condition for the deadlock. But if the resource type requested by the processes forming a cycle and those resources are having only single unit each, then only the deadlock condition can occur. Otherwise, it may be the situation that deadlock condition may not occur. So if you take an example of this particular case, that we have P1, R2 as a resource, P2. There are two processes, P1 and P2, and there are three resources, R2, R1, and R3. So R2 and R1 are having single unit, and P1 has requested to R2. R2 is already assigned to P2. P2 has requesting R1, and R1 is assigned to P1. So it means this is in the deadlock state because both the resources are having the single unit. So if the resources which are available in the system and the resources which are required by the processes, if those resources are having single unit, and if the resource allocation graph represents a cycle, then there will be that cycle, the presence of cycle will be the necessary as well as the sufficient condition for the deadlock. So meaning thereby a cycle in the graph is a necessary condition as well as the sufficient condition for those systems in which the resources are having only single unit. But if the resources are having multiple units, there are many units available in those resources, then in that particular case, the cycle will be a necessary condition, but it is not a sufficient condition as discussed in this particular case. Because if P3 is going to release, R1 will be available to P2. So let us go for another example. So in that case, in which the resources are having multiple units, and if cycle is also present, then what will be the sufficient condition for the deadlock? So for this particular case, second case, in which the resources are having multiple units, then in that case, not will be the sufficient condition for deadlock. And what is not? Not means the resource allocation graph will be having more than one cycle. If there is existence of more than one cycle, then it is going to create a knot, and that knot will be the sufficient condition for the deadlock. So let us take, for the second example, let us take the second one, that in which now P1 is requesting for R2 and it is already holding R1, one unit of R1. P2 is requesting for R1 and R2, which is having one unit, it is already allocated or assigned to P2. P3 is requesting for R2 and one of the unit of R1 is already assigned to P3. Now, if this particular graph is having more than one cycle and creating a knot, then this will be a deadlock situation. See, what are those cycles? P1, R2, P2, R1, and P1. This is one cycle. Another cycle is P3, R2, P2, R1, and P3. This is another cycle. So it means it is going to create a knot which contains P1, P2, P3, R1, and R2. So this, in this particular case, in which the resources are having multiple units, but if it is creating a knot, then that condition will can be said that it is going to be in the deadlock state. So the necessary and the sufficient condition is going to differ if the resources which are available in the system is having single unit, and if they are having single unit, in that particular case, cycle will be the sufficient, necessary as well as the sufficient condition. But in case if the resources are having multiple units, in that particular case, cycle will be the necessary condition, but not will be the sufficient condition for the deadlock. So if you want to summarize it, you can say that cycle is a necessary condition for the deadlock. But if there are single units in the each resources involved in that particular cycle, in that particular system, a cycle can be both necessary as well as the sufficient condition. But if there are one or more resources which are having one or more units, then in that case, not will be the sufficient condition for a deadlock to exist. Now wait for the graph. Now, when all the resource type are having only single unit, if in a particular system, then the we don't try to go for the resource allocation graph. Then we try to go for the some simplified graph. And simplified graph is actually obtained from the original, that is resource allocation graph. And in that particular case, we remove the resource node, and there will be an edge which will be in between the processes in that graph. So that simplified graph, which are being represented in the simplified form of the resource allocation graph, in which the resources are having only single units, are known as weight for the graph. Now, the weight for the graph clearly shows that which processes are waiting for which process. For example, if you're looking for if you look this graph, P1 is asking R2 and P3 is also asking R2, and R2 is assigned to P2. It means P1 and P3 both are waiting for P2 to release it. It means there will be an edge in the simplified graph. There will be an edge from P1 to P2 as well as from P3 to P2. Why? Because the resource which is having single unit is allocated to P2. So it means P1 and P3 are in waiting state, and they are waiting for what? They are waiting for P2 to release. It means P1 is waiting for P2 and P3 is waiting for P2. So this graph will be converted into this form. P2 is requesting for R1 and R1 is already assigned to P1. So until unless P1 is not going to release it, R1 will not be allotted to P2. So it means P2 is waiting for P1. So there will be a graph. So this kind of graph, which is converted from the resource allocation graph to the simplified graph, which is called wait for the graph, is converted. And this conversion, wait for the graph, is done only for that particular system which has the resources, and those resources are having single unit. So this WFG, that is wait for the graph, will be representing that whether there is a deadlock or not. Now, how to handle if there is a deadlock in the distributed system? How to handle it? Now, as far as the deadlock is concerned, in principle, uh, it is very much similar to the deadlock which occur in the distributed system. So as far as the description of the deadlock is concerned, it is holding for the centralized system as well as the distributed system. Of course, distributed system are more complex system because handling of, and that is because of that, the handling of the deadlock in the distributed system is more complex because the resources are scattered, processes are scattered, but in centralized it is confined to some certain place. But in a distributed system, resources are scattered as well as the processes are scattered. So we commonly adopt three strategies to handle the deadlock. The first is the avoidance, second one is the prevention, third one is the detection. Out of this, the third one is the more important besides the avoidance and the prevention. What is the meaning of avoidance? Avoidance means that the resources are carefully allocated to avoid the deadlock. It means we must have a policy of resource allocation so that in case of avoidance, the resources are very carefully allocated just to avoid the deadlock. But normally this avoidance is not able to done. We will see it later on. Prevention, we try to put certain type of constraint so that whenever a process is going to request for the resources, we try to allocate those resources on a certain terms and condition, on a certain constraint, so that the deadlock can be avoided. And third one is the detection and the recovery. Detection and the recovery is it is taken care more instead of avoidance and the prevention, because it is allowed in the distributed system. We try to allow the deadlocks to occur, and then we adopt the detection algorithm to detect it and then try to resolve by a certain means so that it recovers from the deadlock. So now it is not the deadlock which used to occur in the distributed system. It can be distinguished in between two. That is, the one is called the resource deadlock and another is called the communication deadlock. Now, as far as the resource deadlock is concerned, it occurs when two or more processes are waiting permanently for the resources which are held by the other processes. Whereas in the case of communication deadlock, it occurs among the set of the processes when they are blocked just by waiting for the messages which they have to receive from the other processes so that they can start their execution. But if they are not receiving any message, or the message is not in transit even in between the two processes, then that kind of deadlock is called the communication deadlock. So when there will be no message in the transit between the pair of the resources, and none of the, as well as the none of the processes will ever, if there is no message in transit, so no message will be received by the processes. So this implies that all the processes which are available in the form of a set are deadlocked. Now, as far as the communication deadlock is concerned, it can be very easily modeled and it can be rectified also very easily, and can be represented in the form of a wait for graph, because each processes are waiting to receive the message from the other processes. Hence, the detection of this communication deadlock can be done in the same manner as we have adopted the system of the wait for the graph. So wait WFG can be applied for the communication, for detection of the communication deadlock. So out of these three strategies, avoidance, prevention, and the detection and the recovery, we are going to discuss the first one, that is the deadlock avoidance. Now, deadlock avoidance method use some advanced knowledge of the uses of the resources by a particular process, just to predict that what will be the future state of the system, just for avoiding that the deadlock should not occur. So, as far as the deadlock avoidance algorithm is concerned, we used to follow these three steps. The first step is when a process requests for a resource, it is not allocated immediately. Rather, the system assumes that request is granted. So, meaning thereby, whenever there is a request, it is not immediately allocated, but it put itself in a certain stage. Of course, the request is granted, but it is not allocated. So it will take its own time for allocation of the resources to that particular process who has made a request. The second step is with the step one assumption and advanced knowledge of the resource uses of the processes, the system performs some analysis to decide whether the granting of the process's request is safe or not. Meaning thereby, once a request has been received, the request is granted, but it is not still allocated. So what the algorithm will try to analyze that if this resource which is requested by a process has been allotted to that particular process, whether it is safe to do it or it is unsafe. Safe to do it means if it is allocated, then by the analysis it will able to know that there will not be any deadlock situation. And it will be unsafe that if it is going to analyze and find that once this particular resource which is requested by a particular process has been allocated to that process, there may be a situation that it can create a deadlock. And the third step is the resource is allocated to the process only when the analysis of which is being done in the step number 2 shows that it is safe to do it. Otherwise, the request will be deferred. So in the first process, the request is being received, grant may be done, but no allocation. In the second step, it will try to find out, it will try to do the analysis part and try to find out the various safe zone and unsafe zone. And then it will be allocated to that particular process if it is going to move in a safe sequence, or otherwise it is going to defer it. So the new concept has come, that is safe state or safe zone or safe sequence or unsafe state or unsafe sequence or unsafe mode. So let us now look for what is important for that, because safety is the major issue which in the resource allocation. So when it is called the safe system, so a system is said to be a safe system if there is no deadlock state. And if there is no deadlock state, it means there must be certain ordering of the processes in which the resource request and the processes can be granted to run all of them to complete its process. So for a particular safe state, there may be many such processes ordering. There may be possibility, if there are 3 states, there are 4 states, then the ordering may be different. It may be P1, P2, P3, P4. It may be P1, P4, P3, P2. It may be P2, P3, P1, like that. So what is the ordering by which, if we go with that ordering, whether that ordering is safe or not? So any ordering of the process that can guarantee that all the processes will complete its job without intervention, that is called that is known as the safe mode or safe zone or safe state or the safe sequence. Now, how to make this safe sequence? It is based on the idea of satisfying the condition that if the process, all the processes are in safe condition or not. I'm giving you an example. Suppose there are three processes, P1, P2, P3, and the resources available are, suppose there are certain resources which are available. If P1 has been allotted with the certain resource, P2 is allotted with the certain resource, P3 is allotted with the certain resource, and P1 is again asking for another resource. And the available resource, besides allocating the different resources to the different processes, and now the process P1 is asking for more resources. And at that particular moment of time, if the availability of the resources are less than the demand or the request of the P1, then it cannot be granted. Then it has to wait. But if the P1, whatever it is asking or requesting for a resource, and it is available in the form of a balance resource in the particular system, then it can be done. But we have to be very careful before we are going to grant that particular resource, which is again demanded by the process P1, whether after giving, after allocating that particular resource, ऐसा तो नहीं होगा कि the system will go into the deadlock state. So to understand all these three steps which is used in the deadlock avoidance algorithm, it is better to explain it with the example. So this is, I have already explained what is safe state, how the safe state, what is safe state. A system is said to be in safe state if it is not in a deadlock state and there exists some ordering of the process in which the resources request of the processes can be granted to run all of them for completing its job. So now let us go with a particular example. Now in this example, what is already assumed that the system has total eight units of the resources. A particular, there is one resource and there are 8 units available in that particular resource. There are 3 processes, P1, P2, P1, P2, and P3. And they, P1, P2, and P3 are competing together. Now, suppose the maximum unit of the resources which are required by process P1 is 4, maximum unit of the resource required by P2 is 5, and P3 is 6. And they are already holding 2 of the units of the resource. P1 is holding 2, P2 is holding 2, P3 is also holding 2. And they are in requirement of maximum 4, 5, 6. And they are already holding 2, 2, 2. So at this particular moment of time, 2 out of 8 units of the resource, we have 2 free units. Out of these 2 free units, now the analysis part used to happen that if this 2 unit is allocated to P1, which is the actually required maximum requirement of P1, then P1 can complete its job. So what is done? The system does the analysis and allocates 2 to the P1. Once it allocates 2 to the P1, now the P1 will be holding in B. P1 is holding 4, and now there is no free units of the resources. Once the P1 is going to complete its job, the maximum value is going to finish, and it is not holding anything. So we will have 4 free units. Now, out of these 4 free units, either we can go to allot these 4 units. Maximum requirement of P2 is 5, so we can allot 3 units to P2, or all the 4 units can be allotted to P3. So we have 2 way by which we can go. Suppose we have allotted 3 units of available units to the process P2. So the process P2 is requiring 5 maximum, holding, now it is holding 5, and still we are having 1 free. And when P2 will become free, P2 complete its job, it will going to hold nothing, and all the 6 units will be free, and all the 6 units, the P3 which is requiring 4 more units, the 4 units can be given to them. So it is not creating a deadlock. If the second chance, if the second way, if we are going through, instead of allotting 3 units to the process P2, if we are going to allot 4 units to the process P3, then what will happen? We are not allotting it to P2. So P3 is being allotted 4, so it is holding now 4 and free is null. Once it completes its job, it will going to release the hold, and now the out of the 6 unit which has become free just because P3 has completed its job, 3 will be allotted to P2. So in this way, the sequence will be P1, P2, and then P3. Or the other sequence may be P1, P3, and then P2. So it means P1, P2, and P3 is the safe sequence, as well as P1, P3, and P2 is also the safe sequence. So if the ordering is being done in such a manner that first P1 is going to complete its job, then P2 is going to complete its job, and then P3 is going to complete its job, there will be no deadlock. Even though the second safe sequence may be P1 is going to complete its job, then P3 will be completing its job, and then P2 will be completing its job. So in this way, P1, P2, P3, as well as P1, P3, P2 can be the safe sequence of in this particular example. But suppose I'm taking another example. Now in this example, what is the same example which I have taken, the same example is in this case that it is requiring 4, 5, 6 maximum, 2, 2, 2 are already holding, and it is 2 is free. Now, suppose P2 is requesting one more unit. If P2 is requesting one more unit, and without doing any analysis, if the system, without doing any analysis, it gives one resource which is requested by P2 to P2, if it is allocated. So what will happen? Now it will be holding 3, it is still 1. Of course, it is requiring 5, but at that particular moment time, it is asking only for 1 unit. So when 1 unit is given, so it will be holding 2, it will be holding 3, it will be holding 2, and still we have 1 free unit. Now, the situation of deadlock can occur, and this sequence may be molding, may be diverting the safe state into the unsafe state. Now we have only 1 free. Now what will happen? Since P2 is still requiring 2 more, and available is 1, so P2 cannot complete its job. Even though P3 is requiring 4 more, it is not able to complete its job because free is only 1. P1 is requiring 2 more, and we are only having free 1. So all will be not able to complete its job because the availability of the units which are free is less whatever they are in requirement. Even though if P1 is requesting 1 more, 1 can be given, but even though it is not going to complete its process, it's not going to complete its process. So this is going to lead from the system from the safe to a unsafe state. So the important point related about the safe and the unsafe states are very simple, that whatever is the initial state in which no resources are yet to be located, no resources are located and they are yet to be located, all the resources are free, it is always a safe state. Now from a safe state, the system can guarantee that all processes can be run to complete its job. And unsafe state is not a deadlock state, but it may lead to the deadlock state. Just it means that the system cannot guarantee that all processes can be run to the completion as given in this particular example. Now, the deadlock avoidance algorithm basically performs the allocation of the resources in such a manner just to ensure that the system will always remain in the safe state. That is the only idea behind the deadlock avoidance algorithm. This is just the target of the avoidance algorithm. So whatever is the initial state of the system, it is always a safe state. But whenever a process is going to request a resource that is currently available, the system checks to find out that whether the allocation of that resource will be going to change the state of the system from safe to unsafe or not. If not, then the request is immediately granted. Otherwise, it is going to be deferred. So this is all about that what is safe state and what is unsafe state. And but we normally don't prefer the algorithm which is called the deadlock avoidance algorithm, and we have a certain reasons for avoiding the deadlock avoidance algorithm. The first reason is that it is very difficult to know about in advance about the maximum number of the resources which will be in need of a particular process, because the systems are dynamically changing its requirement. Dynamically the demand will be increased, maybe decreased. So it is very difficult to know in advance. The second is the number of the processes is not fixed. It may be three, there may be possibility that there may be four. So three is working and one more process is coming. So it is not fixed because it is going to be varying dynamically with new user is going to log in or existing user is going to log out. Actual number of the elements units which are available, it is also going to change dynamically, because it may be possible that some of the units of the resources are going to break down, and there are certain units which is under repair, which is going to be ready for that. So, and the fourth one is due to restriction in the resource allocation, because we used to put the allocation of the resources as per the request of the processes. We are going to put restriction, so it is also possible that the performance of the system is going to be degraded. So that is all about the deadlock avoidance.